Can everyone hear me? Hey. Awesome. The audio or voice sounds good. Everything's not too quiet or too loud. It's Gucci. All right. Okay. Is there anything anyone wants to talk about, like what we want to focus on or anything before we start, or should we just dive right into this practice final exam and then just run through everything? Run through it. All right. And then binding energy. Okay. We'll talk about binding energy. Okay. For the binding energy, let's see, as we get through everything, we'll go through everything, and then with whatever we have toward the end, we'll cover any extra topics that you want to, such as the binding energy or anything that's related to any of the stuff that we've covered. So going in depth, and then certain points. Okay. Yeah. Again, if you have any questions or anything, just feel free to just throw it into the chat. I'll check it every now and then. And I'll also try to number all of the things that I do, so it's easy for you to just shout out, hey, you know, go to this line, number, whatever, and then just we'll go from there. All right. I'm ready. Let's go. So for this first problem here, we have a double slit experiment. So let's take a look at this. We have two slits that are separated by that given distance and create an interference pattern on a screen that is 2 meters away. Okay, so we have a couple of given pieces of information there. First thing we're going to find is the fifth bright fringe, which is 6 centimeters above the central bright fringe. Find the angle subtended from the slits to the screen. Okay. So let's sketch out this one. Make a very basic sketch of this. Hello, how's everyone doing? Okay, so this is Young's double slit experiment. Okay. So for this problem, so this is for problem 1. We have 2 slits. We're going to ignore the width of the slits, assume that they're very, very, very small. We're not going to talk about it. But we do have a distance between the 2 slits. Let's call this distance between them D. From there to there. And this distance D is again going to be something that's very, very small, something that's very similar to the wavelength of light. It'll be usually some number of micrometers a lot of the time. In this particular problem, if we take a look at this, we have that the 2 slits are separated by a distance of 8 times 10 to the minus 5th meters. It's very close to the order of micrometers. Okay, so we have those slits. And we have a viewing screen some distance away. So slits, and then the viewing screen. Okay. The distance from the slits directly to the viewing screen is going to be defined as the letter L. So let's select L. Like that. also given in the problem. Now, when the light shines through the two slits, so let's say we have incident light going through these slits like this. We'll have one wavelength of light, either given or something we're trying to find. I think in this problem we're going to have to find it at some point. Light will go through the slits and it will interfere, causing an interference pattern because it behaves like a wave. So straight down the center. Okay. If we draw right between the two slits, this line straight to the viewing screen, that will be our line of symmetry. We'll have a bright spot in the center. Okay, we're going to call this m equals 0. This bright spot in that center is going to be m equals 0, and we'll just count the bright spots going outwards. So it'll go bright, dark, bright, dark, bright, and then we'll just mirror that on the other side. Okay. And as we count them, it'll be m equals 1, 2, etc. Now, in this particular problem, they were talking about the 5th bright fringe. So we'll have some 5th one up here, 3, 4, 5, somewhere up here is m equals 5 bright spot. And we have a couple of equations that we can use with the double slit experiment. So first one is going to come from drawing a triangle in here. So you'll have that from the center of the two slits and going out to the point of interest on the viewing screen. So let's say all the way up to m equals 5. Okay. So we have this right triangle right here. And this side length is L. This distance along the viewing screen is always going to be the distance y. It's always measured from the center out to your point of interest. So from here, in our case, we're going to go all the way up to m equals 5. And we're going to call this distance y. In this case, let's subscript it with 5 to identify that it's the 5th order. Okay. Just by using the right triangle, we can actually just write, based on this angle here, how this distance here relates to this distance here. Okay. I see we have a couple of things. No, we're good. Okay. So y5, or just y, is going to be the side opposite to the angle. We have L, which is the adjacent side, so that's going to use tangent. So one equation we're allowed to use here is just tangent theta equals y over L. Let's give these some labels too. Let's call the diagram 1. Let's call this equation 2. The other equation we can use, depending if we're talking about the bright spots or the dark spots, is going to be m lambda. Actually, let me write it this way. D sine theta. It's going to be equal to. It's going to be one of two things. You can split it either into m lambda, so d sine theta equals m lambda, and this is completely determined by whatever you set your coordinate system to, whatever you want to call your 0 or whatever, because you can write this as like plus or minus a half. So let's say if I write this as m, let's use plus a half, for instance, times lambda. Okay. The reason why the plus or the minus isn't really going to matter all that much is that the most important thing is that the stuff in the parenthesis or the m value needs to be equal to whatever it is on the viewing screen. So for instance, for the bright spots, it's just going to be whole numbers, 1, 2, 3, 4, and 5, etc. But the dark spots in between, like here, 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 they're just going to be half integers. In other words, 1/2, or 0.5, 1.5, 2.5, 3.5, etc. So, for instance, let's say if I were to do a dark spot, let's say the first dark spot from the center, which is right after the m equals 0, then it's between 0 and 1. So we know that the value in the parenthesis needs to be a half regardless of what we do. So if I need this value to be a half, then for instance, I would just use m equals 0 plus a half to get myself to a half. If you use this formula with a minus, then the same logic applies where you just need it to be equal to a half overall. So you would just use m equals 1 minus a half to get yourself to a half. So at the end of the day, it doesn't change the fact that these should be 0.5, 1.5, 2.5, etc. Okay? Let me know if there's one version of the formula or the other that you prefer to see it as, just in case, but we'll just continue on with this part of the problem otherwise. So m lambda, you'll use d sine theta equals m lambda if it's constructive or for bright spot. So constructive or bright spot. Both are the equivalent. And then the other one you use for the destructive or for the dark spot in this case. Okay. Let's call this 3. In this problem here, we're going to be talking about the 5th bright spot. So we're going to be using the constructive formula. So m lambda. Okay. So I'm going to pay attention to this part of the formula right here. So let me just write that over here. So part A, d sine theta equals m lambda. Now, in this problem, we need to find the angle that's subtended from the slits to the screen. So we need to find what theta is in this diagram. Now, both equations have theta in it. You'll have tangent theta, and you'll have the d sine theta equation. But in this case, since we know more information about, for instance, the distance between the slits, and we know, for instance, the order number, we might want to go that route. So let's say if we solve for theta in this equation. So theta, actually let me start with sine theta. Sine theta, divide by d, it's m lambda over d. Okay. Now we solve for theta by taking the sine inverse of both sides. So sine inverse m lambda over d. Okay. Let's see here. Let me write down what we're given, which is we have the slit distance. So that's going to be d equals 8 times 10 to the minus 5th meters. And we have that L is 2 meters away. Okay. And actually, we have that the distance to the 5th bright fringe is 6 centimeters. So actually, you might have wondered why I was using the other formula. So actually, we know that y5, the distance from the center to m5, is going to be 6 centimeters. So actually, you would want to use this equation if you had lambda already, but we don't know what the wavelength is. So because we know the distance to the bright spot, we're actually instead going to do the tangent. So tangent theta equals y over L. Okay. So we have y and L. Let's just solve for theta by taking the tangent inverse of both sides. So theta equals tangent inverse of y over L. Most important thing when plugging into this is that the units are consistent. So the values of y and L just need to have the same units. So tangent inverse of y. We could either use y in centimeters with L in centimeters, or we can convert y to meters. It doesn't matter as long as they cancel out. Personally, I'm going to say that L is just 200 centimeters to match those two. So now that's going to be 6 centimeters over 200 centimeters. And let's just calculate what that angle for theta is. Okay, so tangent inverse of 6 over 200 would be 1.72 degrees. So let's call this 4, 5, 6, and then 7. Okay. So again, we're following this route to get to the value of theta, and not doing this since we don't have lambda. Okay. Are there any questions on how I got the answer to part A so far? Otherwise, just give me a thumbs up. Okay, thumbs up. All right, let's take a look at the next part. So the next part we have find the wavelength. Hey, that's conveniently the thing that we're missing to do the other method. So let's use the other equation to get the wavelength. Okay. Let's put this stuff in a big fluffy cloud. So I'm going to just make a little note here. Need lambda use other equation for theta. Okay, so that's again why we didn't do that. Now we are going to use this equation to now get the lambda we were missing now that we have theta. So if we solve this equation, okay, lambda equals d sine theta divided by m. We have the value of d, it's given in the problem. We have theta, we solved for it in the previous part is 1.72, and we have the value of m, which we know it's the fifth bright spot. So plug in. D is 8 times 10 to the minus fifth meters times sine 1.72 degrees divided by 5. Okay. We're just going to calculate this and it will give us the wavelength pretty easily. So we have sine of that angle times 8 times 10 to the minus fifth, and then divide by 5. Especially when you're getting a lot of zeros in the calculator, it's recommended that you switch to scientific mode simply because it's so easy to make a mistake counting all those zeros. So we have 4.80 times 10 to the minus 7th meters. Okay. This is fine as is, but if you want to know what that is in nanometers, we're just going to move the decimal point 2 times, and then it's going to be 480 nanometers. Okay. So either or is fine. Okay. 480 nanometers, if you know the visible light range, which goes somewhere between 400 and 700 nanometers, this is closer to the blue or the violet end of the spectrum. Are there any questions on any of the stuff with this problem or related stuff before we move on to the next one? Let me know or give me a thumbs up. We're good there. All right, let's take a look at the next problem. Okay, This one goes back a bit. These are in no particular order. So the next topic is going to be electricity. So let's take a look at number 2. We have 3 charges, which are in a straight line. Now, this one on our practice test, it seems like she didn't put the diagram in it or the solutions to my knowledge, and also you kind of had to interpret the distances. So what I'm going to do is I'm going to just make one up based on what she has here, and the most important thing is just the concepts. So we'll kind of just piece this together. So we have 3 charges which are given, so the values of Q1, 2, and 3 are given here. They are in a straight line. Okay. So let's just do it left to right. I'll put Q1 on the left side, Q2 somewhere in the middle, and Q3 on the right side. Okay. A lot of these questions in here are having to do with just finding the force that each charge exerts on each other, the total force, and then this last one's more conceptual about if you change the charge from one type to another. So let's sketch this out first. Okay. Let me check and make sure everyone's good. Take a erase. Okay. So let's erase this. All right. So problem 2. Okay. This is going to be for electric forces on point charges. So according to the problem that we have all 3 charges along a straight line. Let's just draw it left to right, and let's just say that positive x is to the right. So we're going to define some coordinate system. So we have a way of saying if it goes to the right, it's positive. If it's the other way, it's negative. Okay. We have 3 charges, and those 3 charges are going to be, we have -2 microcoulombs. So let me write here, Q1 equals -2 microcoulombs. Q2 equals +3 microcoulombs, and Q3 equals -6 microcoulombs. Okay. So from left to right, let's draw these charges. Let's put this one somewhere over here. I'll make up some distances. So let's say that the next charge, which is positive, I'll put that a little bit closer to this negative charge. And let's put the last one, which is a negative charge, a little bit more to the right. Okay. So Q1, Q2, and Q3 left to right. Now, so in this problem, starting with part A, we want to find the magnitude and the direction of the force. Now, because these are charges, we're going to be talking about electric forces. Find the direction and magnitude of the force that Q2 exerts on Q3. So for A, force that Q2 exerts on Q3. Okay. So since we're talking about charges 2 and 3, so we have a charge pair. Anytime you have a charge pair between 2 point charges specifically, you use Coulomb's law to solve this. Okay. So Coulomb's law states that the electric force, let's call this F subscript E for electric force, equals, okay, I'm going to call this generically capital Q and lowercase q. Sometimes they just call 1 and 2, A and B, but I don't want to give this any subscripts because we're going to be using 1, 2, and 3, so I don't want to mix them up. So we're just going to call them 2 separate Qs, divided by R squared. Okay. We're going to recall that K is some constant. It's called Coulomb's constant. And that given value is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Both of these Q's are just the two charges. So Q and Q are defined as the charges, okay, measured in coulombs. And R is the distance that separates those two charges. So R is defined as distance between charges. Okay. Now, diagram, let's call 1. Let's call this 2. And then all these definitions 3. Okay. So what we're going to do is we're just going to rewrite Coulomb's law specifically for the charge pair that we're talking about. Okay. So in this case, since we're going to find the force that 2 exerts onto 3, in other words, find the force on 3, okay, let's write it this way. If you want to change the subscript to whatever charges you're discussing, that's a pretty common thing to do. So what I would do is I'll say force on 3 caused by 2. The order of the subscripts doesn't really matter as long as you know what it represents. So you can write 2, 3 or 3, 2. It's going to mean really the same thing regardless. Equals force, so force on 3 caused by 2 equals K Q3 Q2. So notice I'm just going to change the generic notation for the 2 Q's over to the 2 charges I specifically want to talk about. Divided by R, and let's call that subscript 3, 2 as well to be very specific that it's the distance between charges 3 and 2 as opposed to a different R distance. Okay. Now remember, when you're using this, we're going to care more about calculating the magnitude of this first, and then once we have how large it is, just a positive number, not caring about any minus signs, we're just going to use the picture to determine conceptually which way the force will go, and that's where pluses and minuses will be taken care of. So we don't plug in anything negative into here, just to get its magnitude. So K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. The charges 3 and 2 are given here. Ignoring minus signs, we have 6 microcoulombs, so 6 times 10 to the minus 6th coulombs times charge 2, which is 3, times 10 to the minus 6th coulombs, divided by the distance. So we need to give some distances to this problem, again, because it wasn't originally given, so I'm just going to make up some distances. Possible options or things they commonly do in problems will either be they give you the distance between these 2 charges, 1 and 2, and the distance between 2 and 3. Another thing that they do sometimes is they actually will give one of these 2 distances, and they'll just give the whole distance between the 2 furthest charges. If that's the case, then you can just subtract a couple of distances to get the remaining distance. Okay. I'm going to do what will trip up more people, so I'm going to give one of the smaller distances and the whole distance. Okay. Let's say that the distance between charge 1 and charge 2, let's just call that lowercase d. And let's call the distance between charge 1 and charge 3, let's call that uppercase d. Okay. And I'll give the values for those. So let's say down here, so lowercase d, let's use a value of, let's do something in millimeters. How about 8 millimeters? Okay. And let's call the bigger distance total of 24 millimeters. Okay. So let's say I give those 2 values. Now, pay attention to the distances because, again, the distances they give you aren't always what you're going to be plugging in. So since we want the distance between charges 3 and 2 specifically, 3 and 2 are located here and here. So the distance between them is actually the remaining distance in this particular problem. So what you'll need to do to get the remaining distance is by realizing that this other distance of 8 millimeters in my problem plus this should add up to the total, or in other words, if you take the larger distance and subtract away that other distance, you'll get the remaining distance. So I'm going to write here a little note. Okay. Distance between 3 and 2 equals the larger distance minus the smaller distance in this particular problem. So that's going to be 24 millimeters minus 8 millimeters. Okay. That'll give us 16 millimeters. So when we plug that in, it'll be 16 times 10 to the minus 3 meters. Okay. So now let's just plug this all in and let's calculate how large that force is. So force on 3 caused by 2 equals, you can check all your units. In this case, it should cancel out to newtons, and it is a force in newtons. We have 16 times 10 to the minus 3. Most common mistake is something even I forget to do sometimes. Don't forget to square this. I'll do it in a different color because it's so much forgotten. Okay. So that distance has to be squared. It's in the bottom, times 8.99 times 10 to the 9th. And then we have the charges, 6 times 10 to the minus 6th. And then 3 times 10 to the minus 6th. Okay. So the force that we get on this is okay writing it in non-scientific notation because it's not that large. 632 newtons. Okay. Let me know if you calculate the same thing, or let me know otherwise. Meanwhile, we'll just continue calculating any other things. Okay. So this is going to be the magnitude of the force that charge 3 feels as a result of charge 2 only. We can also take care of the direction just conceptually looking at the picture. So notice that charge 3 and charge 2 are the opposite kind of charge. We have a negative and a positive. So opposite kinds of charges, they're going to attract towards each other. Okay? So since I'm only interested in the force on 3 caused by 2, so stay focused on charge 3, we're only going to draw the force on this one, which will attract to charge 2, so that's to the left. Let's call that force 3, 2. Okay. So if you want to indicate within your answer what the direction is, I would suggest writing beneath it or around it. This force is in the negative x direction, because according to our coordinate system with positive to the right, to the left means in the negative x direction. So that should answer part A. Okay, magnitude and direction of that force. Part B is to find the magnitude and direction of the force that Q1 exerts on Q3 instead of Q2. So again, the force exerted on Q3, same charge, but not by Q2. We're going to do Q1 now. So is there any questions on any of this before we calculate the next piece and continue moving forward? Give me a thumbs up or let me know otherwise. Let's call this part B. So part B, again, we're going to stay focused on charge 3. We're going to find the force on charge 3, but this time due to the other charge, Q1. So we're going to use the same equation, which is Coulomb's law, but we're going to change the charges of interest, and we're going to change the distance out since it's obviously different than the other distance. So force on 3 caused by 1, so F31 equals K Q3 Q1 over R, let's call it 3-1 squared. Now, I did give you the entire distance in this case, so since I gave you the entire distance across the left and the right charge, that is the distance we want to use in this part of the question, because that is the distance between 1 and 3. So we're not going to need to add or subtract anything. So we can just plug this in. So we have, I think I can fit this in. Let's see here, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Charge 3 was, magnitude of it is 6 times 10 to the minus 6th coulombs times the other charge, which is now charge 1, that's magnitude of 2 times 10 to the minus 6th coulombs, divided by the distance separating them, which is the entire distance given, capital D. It's 24 millimeters in this particular problem. 24 times 10 to the minus, and because it's milli again, minus 3 meters. Okay. Let's just calculate this real quick. I'm getting 10.1 newtons for part A. I don't know what I'm doing. We can run a check on this again if you're getting 10.1. If anybody else wants to confirm the value they get, if it's 10 point something or if it's 632, it's possible I miscalculated it. Meanwhile, I'm going to calculate this bottom one, so do a check on that for me if you can. Okay, so, oh, almost forgot again. Don't forget to square the distance. So it's entirely possible that you may have forgotten to square the distance, maybe? Ah, okay, there we go. See, I almost forgot to square the distance too, so. Now, 24 times 10 to the minus 3. Do not forget to square the distance. Okay. It's so easy to make that even I make it, and I've been doing this for years. That's in the bottom, invert it, multiply 8.99, 10 to the 9th, times 6 times 10 to the minus 6th for the first charge, and then the second charge is times 2 times 10 to the minus 6th. Okay, for this one down here, I get 187 newtons. Okay. And that's our answer for that. If you want to check this one as well, but I would think this looks okay because it's within range of the other one. So since the values are not that much different, I would expect that these are okay at this point. So that gets the magnitude of the force again, but we're going to conceptually go back to the picture and then just say which way the force is. So because we're using charge 3 and charge 1, they're the same kind of charge, and that means that they will repel from each other. So that means charge 1 will cause charge 3 to repel to the positive x direction or to the right in this diagram. So force 3-1 goes to the positive x. So we're going to indicate next to our answer it's in the positive x direction. Awesome. So that's the first two parts. Let me finish labeling some of these. I need to stay up with that. 4 calculations, 5, the note is 6, 7, 8, and 9. Okay. 10. Is there anything I've done in the first two parts that you have questions on, or just give me a thumbs up and we'll move on to part C. Cool, thumbs up. Part C. So we're going to find the total force on charge 3. Okay, so notice from the first two questions that both of them ended with the phrase on 3. So on 3, on 3. Okay, this question in part C also says on 3. So the difference between the last two questions and this question is the first two were just finding one particular force, Q2 on Q3, and another particular force, Q1 on Q3. Those are the two forces that are exerted on Q3 individually. This, we just need to total them up. Magnitude and direction. Okay? So we need to be careful with this because total does mean to add everything up, but because you have to care about the directions of things, total can mean that you're adding negative things. So let's see if we erase this out. Okay, so let's see. The total force, I'll call it the net force, sigma F, it's going to equal, now the way I'll write it is based on the diagram. So we have that there's a force F31. Notice that F31 points in the positive direction, so it's a positive force. F32 points in the opposite direction, in the negative direction of the coordinate system. So what we're really going to end up doing here is taking F31, which is positive, and adding, I'll indicate that I'm totaling or summing things up, I'm adding, but now I'm going to add something in the negative direction, so it's technically subtracting. So F31 plus negative F32, or subtracting off F32. We have both of these values calculated from the first two parts. So what we're going to do is we're just going to drop those in. So F31 from the first part, or actually the second part, was 187 newtons. And then we're going to do plus negative. We have 632 newtons. Okay. Let's just take those and subtract. So 187 minus 632. And we're going to get that the net force equals negative 445 newtons. Okay. Now, you could either do it this way, which is if you account for the signs in here, it will give you a direction in the end. Otherwise, if you just take the difference between them and then find the absolute value of it, that's just going to be the magnitude. This does it in one shot for you. So if we box this, what it will mean is that the magnitude, I'll do this in a different color, the magnitude is 445 newtons. The direction is indicated by the minus sign. This means it's in the negative x direction. Okay, and this answer should make sense because F32 is larger than F31, so there's more force from charge 2 pulling it to the left than charge 1 pushing it out to the right. So that means we should ultimately get an answer which pulls charge 3 to the left. Okay. Okay, so easily we just get the net force from that. Let me be specific. Let's call this net force on 3. Let's call this 2 and then 3. Okay. Let's take a look at the last part and I'll wrap up this problem. So last part of this problem, how does your answer to part C change if charge 3 has the opposite sign? So currently charge 3 is a negative value. The opposite sign, it means we're going to change that to a positive value, make it a positive charge, and then answer how does that affect the answer to part C. So remember that most of the time when we talk about pluses and minuses on things, it's going to be something that has to do with direction. Especially things like forces, which have a direction to them, plus a magnitude. When you talk about positive and negative forces, for instance, it's really referring to its direction. So what will happen is if I change this negative charge out with a positive charge, as the problem is suggesting in part D, what will happen is the forces from the other two charges will be in the opposite direction, because if this was positive, instead of attracting to this, it would repel, so F32 would just flip the opposite way. And Q1, I would be negative with a positive instead, and it would go from repelling to attracting. So all that happens in the problem is the directions of both of the vectors for part A and part B just flip to the opposite direction. They don't change in size because the magnitude only depends on how large the charges are, not what type of charges. So we should still get 632, and we should still get 187 newtons for that. It would just flip signs. So ultimately, for this, we'll still get 445 newtons, but because of everything flipping, the answer to part D is that the net force on 3, let's say that this is after, okay, you switch it. It's just going to be positive 445 newtons. Okay, and just to emphasize here, again, magnitude stays the same. On the right here, magnitude is unchanged. But the direction is flipped to positive x. Okay? And then the very brief explanation in words here. So if you were to fill this answer in on a test, you probably would want a brief explanation to back up your answer. If not for points, at least for your better understanding to do the problem. Okay, so this is because F31 and F32 don't change in magnitude and only flip in direction. Are there any questions on this last couple parts, or the problem, or the concept as a whole? Let me know, or give me a thumbs up before we move on to the next problem. If we were only given one short radius, such as R23, how would we solve for the radius of R12? So only given one short radius, so let's say from 2 to 3. So R23 would have been here to here, so you would need at least a couple of the distances in the problem. So in this problem, what I decided to give you was one of the short distances between 1 and 2 and the whole distance that spans across all the charges. That would mean that you would just need to solve by subtracting to get the remaining distance. Vice versa would apply if you were to do the other one. So like if I were to not give you the distance between 1 and 2, but I were to give you the distance between 2 and 3, you would still need the larger distance to subtract away this smaller distance to get the remaining distance, regardless. And then the other option, like I said, was that if you weren't going to be given the whole distance across, what they could do is just give you the distance between 1 and 2 and the distance between 2 and 3. So both of the smaller distances, and then at some point, if you needed to do like the distance between 1 and 3, you would just add the distances to a total rather than subtract it to get one smaller distances. But regardless, you would have to have 2 distances. Unless the problem was asking you to solve for a distance. If that was the case, then that would be a different problem type in this category. So I'm not sure if she's going to have you do something that much different from this, but there are problems where they ask you to solve for like a distance that the charge needs to be at. A common question would be, where do you need to place this charge to have that there's no net force or the force cancels out on it. So good. Okay, so that answers that. Are there any other questions before we move on? Otherwise, give a thumbs up. Okay. Let's take a look at the next one. Okay. All right, this one. So this problem is a photoelectric effect problem. You can already see based on the term work function, that's a dead giveaway that it's a photoelectric effect problem. But so we have the light source with a given power. The power is 4 × 10⁻⁴ watts. Remember that watt is a condensed unit for what the definition of power is, which is energy or work over time, which is in joules per second. So that's what a watt is. It emits a signal with a wavelength of 400 nanometers. So they give you the wavelength. It illuminates a sodium surface, and they give you the work function for the sodium. It's 2.46 electron volts. Make sure you know how to deal with electron volts, because remember, it's a unit of energy, but you need to know how to go back and forth between electron volts and joules effortlessly. I'll write the conversion up briefly after we take a look at this. Part A is we're going to find the maximum kinetic energy. So key terms are going to be maximum kinetic energy of the ejected electrons. So briefly reviewing how this works, especially looking at the later parts of the problem, talking about explaining if something is capable of ejecting electrons, finding the energy of it. Let's talk a little bit about, again, how this works. So, all right, so let's erase this. Let's not knock down the lights. Okay, so now, again, photoelectric effect. So this is problem 3. And this is on the photoelectric effect. So you'll have some material. Let's draw this material as just like a flat, flat piece right here, horizontal. You have light that will come into it. So here's your incident light. Okay. And it will strike the material. The material is made up of a bunch of protons and electrons, but we're going to focus on the free electrons. And the light supplies some energy, and it can give that energy to the electrons to possibly cause them to move. Remember the main ideas behind the photoelectric effect that determine if the electrons will eject from material or not is, so first thing is the intensity, or in other words, the brightness of the light does not determine if they eject or not. Okay. So you could say the light gets brighter, and there is more energy in brighter light, but there's something deeper beyond it that will pop off the electrons or not, which is the second point, which is that increasing the frequency, okay, increasing the frequency of the light, in other words, an equivalent way to say that based on the equation C equals lambda F would also mean shorter wavelength. I'll abbreviate as lambda. Okay, increasing the frequency, or in other words, making the wavelength shorter, is another way of giving the light more energy, and this is what determines if the electrons pop off or not. So we'll, at some point, eject electrons. Okay. So the ideas behind this was that you want to think of the particle nature of the light, which is to treat them like photons, and realizing that increasing the intensity or the brightness will only basically mean you throw more photons at it. Increasing the frequency will actually give each individual photon more energy. So let's say if you only take one photon and you throw the photon at the material, so what will happen is if it has a high enough frequency, that one photon will have enough energy to just eject an electron, okay, regardless of how many photons you have. But if you took a bunch of photons and each one didn't have enough energy, so let's say you take red light, which doesn't have too much energy by comparison to like violet or ultraviolet. You take a really, really bright red light, tons and tons of red photons, and you throw it at the material, it won't care. It won't eject electrons. So what can happen though is where the intensity will matter is, let's say that if the frequency was high enough, okay, so let's say hypothetically the frequency matched, or the wavelength matched with that of violet or ultraviolet light. What will happen is the electrons will start ejecting, but what will happen is if you make the light brighter or more intense, so you start throwing more and more photons, which individually can eject the electrons, increasing that brightness or intensity will eject more electrons. So again, the intensity will not determine if they eject. It's the frequency that determines if they eject or not. Okay? So that was a conceptual review of that. And remember that the equation that follows this is that the energy of ejected electrons is E equals HF minus the work function. Okay? A lot of times it's W naught again. Sometimes it's with the Greek letter phi. So you have that. Let's call this 1, 2, 3, and 4. Now, one more detail I will go over with this equation. I'm going to discuss this in the next part of the question. So right now, let's answer the first part and see what we can do with this. So again, definitions here, H is Planck's constant. And it has a value of 6.626 times 10 to the minus 34th joules times seconds. F is the frequency. W naught is the work function. Now, if you look at the units of everything, work function of material, looking at the units of everything, H is typically in joule seconds times a frequency, which is in hertz, which is the same as 1/seconds, cancels out to joules. That means in this equation, if you choose to use Planck's constant in joule seconds, it must mean that the work function has to be in joules. So in this problem, they didn't give the work function in joules. They gave it in electron volts. So the first thing we're probably going to need to do is to take that electron volt value for the work function and change it over to joules. So the work function in this problem was given W0 for sodium, and that was a value of, it was 2.46 electron volts at the top here. So 2.46 electron volts. 2.46 EV. Okay. The conversion between electron volts and joules, I'll give it right here. This is important to know. 1 electron volt. Okay. If you want the context of where this comes from, electron is referring to charge, volt is referring to voltage or potential difference. If you dig back through all your equations, there's one equation for potential energy, which says potential energy equals Q times V. That's where this comes from. 1 electron has a value of 1.602, if you need to be that specific, times 10 to the minus 19th coulombs, times 1 volt, which will make a joule. So that's why this conversion factor really just takes on the value of the charge of an electron or proton. So if you can remember the charge of the electron or proton, it has the same value in the conversion. Okay? So we're going to use this and we're going to convert this over. So 2.46 electron volts on top in the numerator. Set up a conversion bracket. Bottom needs to cancel units, so we're going to use 1 electron volt from this conversion, and on top we're going to write the other piece, which is 1.602 times 10 to the minus 19th joules. This will give us an answer in joules. Expect your answer to be small because we're using a very, very small number from the charge. So 2.46 times 1.602 times 10 to the minus 19th is 3.94 times 10 to the minus 19th joules. Okay. Now that we have the value of the work function in joules, we can use it in this equation to solve things now that the units are consistent. So again, going back to what we wanted out of this problem, we wanted that maximum kinetic energy of the ejected electrons. Okay? So when it's referring to the kinetic energy of the ejected electrons, it's referring to the energy in the equation we wrote out. Okay? So we're going to solve for E, which is already solved for. We just need to plug and chug, so to speak. We don't need to move anything around, just write E and plug in. E equals Planck's constant. Okay, so Planck's constant is, let's see here, 6.626 times 10 to the minus 34th joule seconds. We need the frequency of the light. If we're not given the frequency, we need to be given the wavelength because they're very closely related to each other. Now in this problem, I think it was the wavelength that was given. You can see at the top here, the wavelength is 400 nanometers. Okay, so what we're going to do is we're just going to simply change that over to a frequency. So because it's light that's moving, we're going to use the speed of light to convert that over. So let me do this on the side let's do this real quick. We have it's C equals lambda times F, okay? Remember this equation that we used when we talked about light as a wave. We're going to solve for the frequency. So the frequency is lambda over C. Okay. Sorry, other way around. Frequency is C over lambda. We're going to take this. We can either just calculate it right now, or we can drop it into here. I'm going to calculate this value right now just because we might be using this frequency again later, so it might be semi-important to know this frequency for this problem. So we have 3 times 10 to the 8th meters per second. That's the speed of light, remember that, divided by the wavelength, given the problem is 400 times 10 to the minus 9th meters because it's nano. This is borderline edge of violet or getting towards ultraviolet for reference. This is equal to, so we have 400, 10 to the minus 9th, and that's in the bottom, multiplied by 3 times 10 to the 8th. So we have 7.5 times 10 to the 14th. Units will cancel out here for the meters, and you'll only be left with 1 over seconds, which is the same thing as hertz. Okay. I'll write hertz here, but when I plug this in, I'll write 1 over seconds to emphasize how the units cancel. So plugging in there, we have Planck's constant again, times 7.5 times 10 to the 14th, 1 over seconds. Check, make sure we're good there. Okay. So that's H times F, and then we're going to subtract off the work function, which we calculated in joules. So minus 3.94 times 10 to the minus 19th joules. Okay. Let's run this calculation for E. Let me label these. So 5, 6, 7, 8. Okay. So we have the seconds will cancel out here. We're left with joules. Joules minus joules will give us a value in joules. That value for the frequency times 6.626 times 10 to the minus 34. That value minus this value is 3.94 times 10 to the minus 19th. Okay, so the answer for E that we get, the maximum kinetic energy of the ejected electrons, is 1.03 times 10 to the minus 19th joules. Alright, so maximum kinetic energy of electrons. Okay. This works out part A. Are there any questions on part A before we continue moving forward? Let me know or give me a thumbs up. Let's see here. All right, so part B of this. Okay. Part B is determine if light with a frequency of 6 times 10 to the 4th hertz is capable of ejecting electrons. Must give an explanation. This one definitely requires an explanation to work out why, if it ejects or not. So 6.0 times 10 to the 4th hertz. Now, this is why I mentioned that you really need to calculate the frequency at some point here, so you have something to compare to. We're going to need a frequency to compare to because remember conceptually in this problem that if you have too low of a frequency, you won't have electrons ejecting. But as you increase the frequency, at some point the electrons will eject. We need to determine exactly what that frequency is. Once we get that frequency, we'll be able to answer if this frequency is sufficient to eject the electrons or not. So 6 times 10 to the 14th, let's write that down on the side. Okay, let's erase over here. Okay, so part B. Does frequency equal 6.0 times 10 to the 14th hertz eject electrons? Okay, so we noticed in the previous part that when we used a frequency of 7.5 times 10 to the 14th hertz, it did eject electrons, and you can tell that it ejected electrons simply because we got an energy value out of the equation for the maximum kinetic energy. What will happen is as you continue to decrease the frequency, at some point this energy drops down to 0. And if you continue decreasing the frequency, you're not going to do anything at all because it's already ejecting with 0 energy, which means it's not ejecting really. So we need to determine what's called the cutoff frequency. So determine what's called cutoff frequency at which no electrons eject. So the cutoff frequency is again referring to if you have a frequency larger than this, it will eject electrons with some energy. If you are below this frequency, you won't eject electrons at all. So the cutoff frequency is the precise frequency at which they will have 0 energy, just to start with, and if you give it any more than the cutoff frequency, just a little bit, it will give it something larger than 0. So we need to use the same equation, and we need to solve for that cutoff frequency f, setting E equal to 0. So set E equal to 0 to find frequency cutoff. Okay. Sometimes this is just called F0 or F0. Whatever you want to call it, it is going to be the cutoff frequency. So in the equation, we're going to set E equal to 0 and then write the rest of the equation. Okay. That's the equation with it set to 0. We need to solve for F, which is going to be the cutoff frequency. So F, we're going to add over the work function to the other side. And we're going to divide it by Planck's constant h. Okay. If you want to just jump straight to this is fine. But it's good to recognize that this is where it comes from. So this is suggested that you do this, but otherwise you get that. So now at this point, again, work function's got to be in joules if your Planck's constant also has joules in it. So we need to use the value we found, which was 3.94 times 10 to the minus 19th joules for the work function. And we're going to divide it by Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. Okay. Let's calculate this out, and then let's see what we get for the frequency. So we have 6.626, 10 to the minus 34. That's the bottom. And then the top is 3.94, 10 to the minus 19. Okay. The frequency I get, so the cutoff frequency is 5.95 times 10 to the 14th hertz. Okay. This is that special value for the frequency for sodium. If we compare the frequency of light that we're being asked about in the problem to the cutoff frequency, notice that the frequency of light that we're shining onto the material is larger than the cutoff frequency. Because this is the case, the answer is yes, they do eject from the material. So briefly, because if we call this one F, because F is greater than F cutoff, electrons will eject. Then this is exactly why you need to have an explanation for this, because it's a very conceptual part of the problem. It's really just based on your understanding of how the photoelectric effect works. Hypothetically, if there was a value for F given that was less than 5.95 times 10 to the 14th hertz, or whatever it is in your particular problem, then the answer would change to no, they would not eject. Okay. Let's see here. Let's take a look if there's any other parts to this question. And then we only have one last part here. So for the last part, find the energy of each photon, so energy per photon, and calculate how many photons are emitted by the source in 1 second. So we need to write down a few things. There's a couple things we're going to need to calculate. We'll do it one at a time, and we'll go from there. Okay. Okay. So let's, before I erase the right side of this, are there any questions on anything I've done so far? Let me know. And then we'll start part C in 10 to 15 seconds. Okay, good there. All right, I'm gonna erase the right side, and actually I still need to keep up with this. In case that helps you to tell me where to go to. Okay, so part C. We need to first find the energy for a single photon, or the energy per photon. Anytime you want to talk about the energy of a photon, it's a very simple equation, which actually you'll find part of it in the equation we just used. It's the HF part of it. So E equals H times F. Okay, this is the energy of a single photon. So all we need to do is plug in the frequency that we're supposed to use for this. Now, actually, there was a wavelength given in the problem, and then we had a frequency that we used in the last part. Let's double check which one we're supposed to use. It says here, again, find the energy of each photon. Now, it doesn't seem like it's being specific about which one we're supposed to use, because there is the part B frequency to compare, but the original top part of the problem does use the wavelength of 400 nanometers and illuminates the surface. I would ask for clarity on this problem if it was an exam problem. Regardless, all you need to do is plug in a frequency and calculate the energy of the photon, but if you need extra specifics, I would ask about that if this was on the exam. I'm going to roll with the 400 nanometer wavelength, and let's just use that to show an example calculation of getting the energy of a photon. So let's go from there. So if the wavelength equals 400 nanometers, okay, which then means the frequency that's associated with that wavelength, which we solved before, I believe it was 7.5 times 10 to the 14th hertz. Correct me if I'm wrong, but I believe it was that frequency there. So then what we're going to do is just say that E equals Planck's constant, which is 6.626 times 10 to the minus 34 Joules seconds times the frequency, 7.5 times 10 to the 14th. I'll write 1 over seconds to show the cancellation of the units. And let's calculate this out. Energies of the photon are going to be really small, like -19 or around there for the power. Let's do this. We have 6.626 times 10 to the minus 34 times 7.5 times 10 to the 14. So we have 4.97 times 10 to the minus 19th joules. It's in the ballpark that we expected it in. Okay. So the answer is this, and the problem did not specify that it wanted it in anything, you know, joules or electron volts, so you're kind of free to do whatever you want. If you did for some reason need this in electron volts, just reference to the previous part where we converted using electron volts to joules and just do the opposite to get this back to electron volts. Otherwise, this is fine. Okay, so that's the energy for one single photon. Okay, understanding that this is the energy for one, emphasis on one photon, will help you to answer the next part of this question, which says to calculate the number of photons you have. So specifically, in this problem, we were given a power value at the very beginning in watts. So if we look back here, you can see at the top that it says a light source of power 4 times 10 to the minus 4th watts. Okay, why is power important in this problem? Well, power is directly related to energy or work. So let's just call that energy. But it's not just energy, it's energy per amount of time. So if we can get the amount of energy from a certain time using that power, we'll have a total energy. Then we can take that total energy and we can compare it to the value of the energy per photon. What will happen is you'll have a lot bigger amount of energy total, and you'll have the energy of a single photon, so you just find how many times that energy of a photon goes into that total amount, and that's the number of photons. So let's write this out. So power is 4 times 10 to the minus 4. I will write it in joules per second just to emphasize the relationship here. So joules per second to emphasize its energy per amount of time. Okay, that's a watt. Recall that the definition of power is very straightforward. Okay. Power, again, equals energy or work. I'll write E for energy. Okay. Over time. call it delta T. Okay. What we want out of this is the energy that's emitted over 1 second, because the problem stated that we need to find how many photons are emitted in 1 second. It doesn't have to be a single second. The problem could have easily said 5 seconds, a minute, which you'll convert to 60 seconds, etc. We solve for E, which is we move the time over and it's power times time. So P times delta T. Okay. So the power is 4 times 10 to the minus 4th joules per second. The time in this specific problem is only 1 second. Again, could be any value. So we're only going to use 1 second, which means we get the same value, but it's just that many joules. So 4 times 10 to the minus 4th joules. Okay? This is the total amount of energy associated with the beam in 1 second. Okay, so energy of light beam in 1 second. Okay. Now that we have the total energy in the light beam per second, we're going to compare this value to the energy per photon. So notice that the energy per photon is significantly smaller. It's 10 to the minus 19th compared to 10 to the minus 4th joules, which still isn't that much energy, but comparatively speaking, it's a whole lot more energy. So we can fit a lot of these into that. So what I'll do is I'll write over here simply that, let's call it the number of photons n. There's no specific formula that may be given for this, but it's just something you're supposed to reason with. So let's call this n, okay? The number of electrons is, I'm sorry, when I say electrons, I mean photons, really. Number of photons is the total energy divided by the energy per photon, okay? And that gives us the number of photons. Okay. All right. Total energy is 4 times 10 to the minus 4th joules. Divided by the energy per photon is 4.97 times 10 to the minus 19th joules. Okay. Let's calculate this out. Notice the number of joules, or the units joules cancel, leaving you with essentially unitless. What you can do, if it helps you to see how this works out to number of photons, is to throw in a dummy unit here, which is joules per photon, where photon doesn't really count as a technical unit. We're using it as a dummy unit just so we get photons in the end. So the fraction will flip, the joules will cancel, and you're left with photons as the unit. So this equals, so that number, and then we have times 4 times 10 to the minus 4th. Okay, we get 8.05 times 10 to the 14th photons. And that is a ton of photons. Okay. Is there any questions on this part of the problem or any other concepts pertaining to everything we've done with the, I think it was the photoelectric effect? Let me know or give me a thumbs up and we'll move on to the 4th problem. let's see here. So next one. Okay. This one deals with optics. So in this problem, we have a person with a given near point. Okay. The near point distance is given. The near point, by the way, as well as the far point, they're referring to points that the eye is able to focus on something. So the near point is the closest point that an object can be brought to and still be in focus for the eye. Bring it any closer and it's out of focus. The far point is the other way around, where it means that the furthest you can move to the object until it becomes out of focus if you push it any further. Okay. So we're given the near point distance. They wear glasses to allow them to read a newspaper. So we're going to treat the newspaper like some object in our problem. It's held 26 centimeters from their eyes. And this part where it says to assume that the glasses are next to the eyes, what it means is that there's going to be some distance between their eyes and the glasses, but that distance is very, very, very small compared to the other distances in the problem. For instance, the distance the glasses might be away might only be a centimeter. So that distance is small enough compared to the other distances that we don't need to care about it. So a few things. We're going to find the focal length of the glasses that they're wearing, and we'll go from there. Okay. So one thing to remember about when glasses are worn, there are some mechanics behind how this works, but the end of the story here is that when you have someone wearing glasses, you're going to remember that when you use the distance for the object that you're talking about, the newspaper, this 26 centimeter distance, what they see with their eyes is a virtual image. The important thing about virtual images is that the distance used has a negative value. That will explain why we'll use a negative value for one of these distances. The near point distance will serve as our other distance. Okay? For that, we'll just use a very simple equation to solve it. Okay. So let's see here. Let's erase this part here. So problem 4. So this deals with optics, specifically lenses. Okay, you have lens systems and you have mirror systems. So make sure you know how to do both of them if it wasn't clarified if you need to do one or the other. So for lenses, we have the thin lens equation. Okay. The thin lens equation is 1 over f equals 1 over dO plus 1 over di. Okay. This is actually also the same equation that's used for the mirrors as well, so you can use this for both the lens and the mirror. The main distinction is going to be that for the mirror, you're going to have another equation that talks about the radius of curvature and how you'll divide it by 2 to get the focal length. For the thin lenses, we don't have that, so it's just this. There's other equations such as the magnification that you can use for both of them, but we'll get to that in the next parts. So in this problem, so here we have the near point distance and the newspaper some distance from their eyes. So let's say if we have the newspaper is seen to be 26 centimeters from their eyes. So we have that a value for dO and a value for di. So you have the near point distance is 120, and then the newspaper is 26. Okay. So let's see here. So the object distance, actually, I think for this problem, if you hold the object at that position, then actually, so the object distance should be 26, I believe, 26 centimeters. The near point would be, I believe, where the image forms. So you would have minus 120 centimeters for that. The minus is going to come again from the fact that you're going to get a virtual image from having eyeglasses, regardless if it's far-sighted or nearsighted, whether if you're talking about the far point or the near point. Okay, so make sure you don't forget the negative. The focal length, 1 over f. So actually, you can do one of the following. You can either plug it in and then just remember to flip the answer in the end, or you can just flip both sides now and then drop it in. I'm going to flip both sides now so I don't forget. It's 1 over all of this stuff. Okay. So we have 1 over DO is 26 centimeters. Okay. We have plus 1 over negative 120 centimeters. Okay. Plug these in and we'll get a value for the focal length of the lens. Okay. So we have 1 over 26 plus, which will ultimately be subtracting it, so minus 1 over 20. 120. Get a value there, and then do 1 over that answer. So we get that the focal length is 33.2 centimeters. Okay, because we've used centimeters in all of the values that we plug in, units are all consistent. It will just give us something in centimeters. So the only thing that matters here is consistency. You don't need to convert if you don't want to. Okay. Now, also pay attention to the answer that you get here. Notice that, for instance, here, the focal length is positive, okay? So a little reminder on the conceptual details of lenses is you'll have 2 main types of lenses, okay? So types of lenses, okay? You have what's called a positive or a converging lens. There is a specific shape that we use a lot in this class, which is what's called double convex lens, where it sticks outward on both sides. So this lens here, so the terms are either double convex or positive or converging. Okay. All of these work for that shape, and that means that the focal length is positive. Okay. For the opposite shape, where the surfaces will bend inwards toward the center, that will be the double concave. It's a negative lens or diverging. Okay, and that means the focal length is negative. Okay. Notice that because the answer is positive, it suggests that the person needs a positive converging or a double convex lens where it sticks out on both sides. If you look up someone who has a near point, and so in the context of the problem, we were talking about a person with a near point distance and allows them to read something which is closer than their near point. So this person can see farther away, but they can't really see closer, so they're farsighted. This is called, I believe it was hyperopia, if I'm not mistaken. Yes, so farsightedness is called hyperopia. I'll write that out in a second. And you're going to need a positive or converging or double convex lens to correct this. So this answer does make sense for this particular problem. Okay, let me write that out. So we have Let me write out, based off of the last part of the question, actually, there's a term even I haven't seen before. It's called, so ailment. It's the ailment, okay? This word, apparently, when you look it up, has to do with like a sickness or something. In this case, it's referring to the type of eye defection or impurity that they have. So since they are not going to see things that are really close, it's farsighted or hyperopia. So we have farsighted, okay, which is hyperopia. I believe that's how it's spelled. Okay, this needs F being positive. Okay, so you need this type of lens to correct that. The other one is nearsighted, which is not this problem. So a problem, an equivalent problem you should think about if you're going to study this problem is, what if you changed it to a nearsighted problem instead of a farsighted? So instead of giving you a near point, the problem could give you a far point, and you have to solve it a little bit differently. This one is myopia. Okay. This one needs focal length being negative. Okay, so you'll need the other type of lens to correct that vision. So if you were to do the same problem for the nearsighted case, you should get a negative focal length for your answer instead of the positive focal length. Okay, and in either case, farsighted or nearsighted, when you're talking about the glasses, you want to also talk about virtual images. Okay, so virtual image implies that the value of the image distance is negative. Okay, that's a very important point in solving this problem. So that's why I was using the negative 120 centimeters. When you wear those prescription glasses, you'll have the virtual images in this problem. Okay, so those are some good details to take note of when you're doing these problems. Now, so I think we've finished that first part. We found the focal length. Let's take a look at this next part. Part B says, if a picture in the newspaper is 2 centimeters high. Okay, so now in the previous part, we treated the newspaper as the object. Now, in this case, we're talking about something in the newspaper. So specifically, the object is something in the newspaper which has that size of 2 centimeters. Find by how much it has magnified and the height of the image. Okay, so let's start with the magnification. Okay. So the magnification has a definition. Magnification. Okay. We use M to abbreviate for magnification. The definition of it is the height of the image, HI, divided by the height of the object, HO. If you cannot use enough information about the heights to get the magnification, or use any of these to get any of the other remaining things you don't know, you can also realize that it's also equal to negative DI, the image distance, divided by DO, the object distance. So we'll use this to calculate the magnification. In this particular problem, you don't know enough information about the heights of the images, so they'll give you the object height in this case, but you don't know anything about the image height and you don't know the magnification, so it's not enough to do anything with it. But from the previous part, you'll have either solved for, or you'll already be given what these are. So in most problems, you'll be given like the object distance and like a focal length, and you may have to solve for an image distance. But at this point in the problem, however you got that information, whether if it was given or if you've solved for it, you should have it at this point. So we're going to use this to get the magnification. So the magnification equals negative DI. The image distance is again negative 120 centimeters divided by the object distance, which is 26 centimeters. Again, The only thing that matters here is the consistency of the units. They're both in centimeters, so they both cancel out properly. Okay. So 120 over 26 is 4.62. Okay. Because the units cancel out and there's nothing left, this is a unitless number. Okay? So this is unitless just to say that the magnification value is just how many times bigger or how many times smaller the image has gotten. So in this case, the image is 4.62 times larger than the object. So we can now use this magnification to tell us how big the image actually is. So for instance, if the object height is given in the problem and we know it's 2 centimeters, then this implies we're going to use this part of the equation for the magnification. So magnification's definition is height image over height object. So if we take the magnification equation and just solve it for HI, height of image is magnification times the height of the object. This equals 4.62 times the height of the object, which is 2 centimeters. So we just multiply that by 2. We get 9.24, I believe, okay, centimeters. And that is the final image height. Okay, so from this information, you can also determine the image type if you need to discuss it. Let's say if the problem talks about describing the image. Actually, in this problem, they don't ask about the image description, but you should know how to do it. So in here, if I were to ask what's the description of the image, you should be able to answer that, because the first description is it real or virtual? That's the type of image. We can answer that because we know the image distance, which determines if it's real or virtual. So in this problem, it's going to be virtual. The magnification is one way of telling what happens to the orientation, if it's upright or if it's upside down, and as well as the size of it. So if the magnification ends up being a positive value, the image is upright, so it's standing like this. So in this case, it's an upright image. If the magnification was negative in a different problem, it's inverted or upside down. Then the other thing you pay attention to is how big is the magnification, so the absolute value of it. Because the absolute value of this is just 4.62, if it's larger than 1, it's going to be an enlarged image or bigger. If it's a magnification of 1, it means it's the same size. And if it's less than 1, it means it's reduced or shrunk down. Okay. So make sure you know all of the image descriptions and knowing how to pick them out. That's one thing that's important to know with these problems. As for the last part of this problem, we kind of discussed it here already. So in this particular problem, okay, they are farsighted or have hyperopia. Okay, and that's the answer to part C. And the reasoning is because they were talking about a near point, and you need this positive lens to correct that. So that means they'll be able to see farther, but not closer. Okay. Let me know if there's any questions you have on this problem or related ideas, and then let's move on to the next problem. Okay. And then we have the last one. The question for this last problem. So on the problem for how do we know if it's real or virtual? So that was based on, so value-wise, that was based on the image distance. So if the image distance is positive, it's real. If the image distance is negative, it's virtual. That's directly what determines the image type. Ray traces are a whole different story, and there's another way to determine image descriptions based off of doing a ray trace. I covered that on yesterday's live stream. You can go play that back. It was, I think I did the problems in order from the last topic to on the first topic, so you probably find it on the second or third problem, how to do a ray trace for at least a mirror. I'm not sure if she cares too much about ray traces, but make sure you know how to do the ray traces for the different systems if it's the case, and then knowing how to figure out the image type based on your drawings too. So that would be the other way of determining if it's real virtual, the size, the orientation, etc. But otherwise, just for real virtual based off of the numbers, it's just the image distance. Let's see here. We're doing okay on time. I think, yeah, we should be able to finish everything before midnight, and then we could still go on a little bit if we want to talk about anything else possibly. But let's shoot to at least finish all of this stuff. I'm going to intend on possibly doing at least one more live stream tomorrow or Tuesday. We can discuss that a little bit further, and we can do anything else if we need to. For now, question 5. So we have this modern physics problem. So this is dealing with quantum and like the hydrogen atom energy levels. So we have here an electron in a hydrogen atom. Okay, is initially in the n equals 5 state. Okay, so we need to talk a little bit about the hydrogen atom, or just atoms in general, and energy states. And we're going to talk about how the electron will lose a certain amount of energy when it makes a transition from one state, which is the n equals 5 state, to a lower energy state. Okay. In this one, it wants us to find the quantum number n, also known as the energy level or energy value. So let's write some of this stuff out. Okay. I'm going to erase this. Okay, so let's write out a couple of things. So for this type of problem, so problem 5. Okay, so we have hydrogen atom. Okay. So we have in the atom, there's going to be the center part, which is the nucleus. Okay. Now, depending on the type of atom you have, you'll have a different number of protons, neutrons, and electrons. Most common problem will be a hydrogen atom problem. It's not a big deal if it was any other materials. You know, if you took something instead of hydrogen, it could be helium, other things in the periodic table. But let's stick with hydrogen for now. So we have in hydrogen, there's one proton in the nucleus. Remember that the number of protons will define the what it is. It's also known as the atomic number. So the atomic number is the number of protons, is your element. So for hydrogen, in the nucleus, okay, we say that the Z value equals 1. So the Z value is the atomic number, or the number of protons. So atomic number or number protons. Okay. There's also technically neutrons in the nucleus, so you could talk about neutrons being in the nucleus as well. Then you have different energy states. So we have these orbitals with different n values out here. Okay, so this would be like n equals 1, 2, 3, etc. So in this problem, it says that the electron is in the n=5 state. So we're going to go a little bit further out. Since it's only 5, I can probably draw that and get away with it without being too big. So we'll have an electron all the way out in this orbital. Okay. There's your electron. And it's initially in that state. What will happen in these problems is you'll have an electron in a higher energy state, and it will move down to a lower energy level. And as it loses energy, as it drops down, it will emit light as another form of energy. So how you determine what that wavelength of light is, there is one equation that you may talk about here, which is the Rydberg equation. Okay. So if you want to talk about that wavelength of light or the frequency of that emitted light, it's 1 over lambda equals r times, let's call this n prime squared, could be n final, minus 1 over n squared, which could be 1 over n initial. So in this equation, lambda is the wavelength of the emitted light, r is the Rydberg constant, and it's equal to a value of 1.097 times 10 to the 7th, 1 over meters. Okay. N is defined as the initial higher energy level, and n prime is the final or the lower energy level. And this would assume that you are going from a high energy state to a low energy state so that you emit light. What can happen sometimes, though, which would not be this problem, is you could have that an electron starts at a lower energy state, a photon or some light hits the electron and it takes in some of that energy and it causes the electron to jump up to a higher energy state. So in one direction, going from low to high, it will take in light and move it to a higher energy state. In this particular problem and in what you want to study, it's going to go from a higher energy state down to a lower energy state, and it's going to emit light instead. Okay? This is what you would use if you wanted to talk about that wavelength. Now, notice in this problem, though, they talk about also the specific amount of energy, which is another equation that we could list off. So the amount of energy for a particular energy state is the following. Call this E subscript n equals. We have that's negative z squared over n squared times 13.6 electron volts. Okay. So this equation here will give us that energy value, and according to the equation, when it has the 13.6 electron volts, it's going to tell us the energy value in electron volts, because this is unitless and this is unitless. So get a value in electron volts, and it will be associated with that particular n value for the orbital. So in this problem, we have that we have the electron initially in the n=5 state, so we know the value of n. The electron loses a certain amount of energy, 2.86 electron volts, and it makes a transition to the lower energy state. We want to find the value of n that corresponds to what energy state it dropped down to. So remember in these problems that conceptually these energy states are quantized. So quantized meaning that they come in discrete or set amounts, intervals. you can have 1, 2, or 3, but you can't have anything in between them. So you can't have like 1.5 or 2.5 or 3.7. It's 1 or 2 or 3, nothing in between. Okay. So when you're looking for an answer to this problem, when it's asking you to find the value of n it goes to, you better not be getting like 2.5 for the answer. It's either going to be like 2 or 3. The problem should be designed so that if you use all the values appropriately, you should be able to get something like 2.999 or like 3.001, which is practically something like 3. So let's start by taking this equation and using n equals 5 to determine how much energy there is in that energy state. The reason we want to do that is because the problem stated that we lost a certain amount of energy in electron volts. So what we can do is we can calculate the energy in the higher energy state in electron volts. We can take the energy and lose some amount, calculate what that new energy value after we lost it is, and for that new energy value, calculate the corresponding n value. So we're going to end up using this equation twice. Once to calculate the energy level, after you decrease the energy, then resolve it for n for the other level. So plugging this in, we're going to say E, let's call it E5, equals minus Z, again, is the atomic number. For hydrogen, in most problems, it's just going to be 1. The next one would probably be helium if you had anything other than hydrogen. Helium would be 2, for example. But it's the numbers in the periodic table, and for hydrogen, you should know it's 1. So 1 squared is just 1. Divided by the energy level is 5 squared times 13.6 electron volts. Okay. So we're going to take 13.6 and then over 5 squared, which is 25. So we have, it's 13.6 over 25, and it's negative. So we have E5 equals negative 0.544, and then the units carry through to be electron volts. Okay. So we have the energy associated with the energy level for 5. We were told that we're going to subtract a certain amount, so we're going to say, okay, it makes a transition to a lower energy level, so the delta E value, delta E meaning just how much energy we lost or gained, or change in energy, is negative 2. Let's see, we have 2.86 electron volts. Okay. We're going to take E5, add delta E to it, which actually means subtracting off 2.86 because the delta E is a negative value. And it will give us a new value. We don't know what energy state it's in, so we're going to just keep calling it N. Maybe call it En prime or something like that, so it indicates it's the final energy state. We don't know what that value of N is, but we can say it's going to be E5 plus how much we changed it by, which is going to be negative 0.544 electron volts plus negative 2.86 electron volts. Taking these two numbers as a negative and an even more negative is going to make a larger negative number. So we have that number minus 2.86, and that gives us negative 2.316 electron volts. Okay. This is the new energy value corresponding to the unknown energy state. We're going to recycle this equation again and now solve it for N instead of E. So solve for N in the equation. So what we're going to do is we're going to swap places between the energy value and the N value. So we're going to multiply by N to the left side, and we're going to swap it out with E down below. So we should just get N squared, which all you have to do in the end is square root it. So write what we have, and then we'll square root it. So minus Z squared over the unknown energy state value, and then 13.6 electron volts. Okay, we've solved for n and then not forgetting to square root it. That is one of the mistakes you could possibly make. If you're calculating your n value and you find that you're not getting an integer number like 1, 2, 3, or 4, one mistake you could have made, which is pretty common, is to just forget to square root it. So that's one place to look. So we take, in this case, it's just going to be square root of -1 squared, because again it's hydrogen, divided by the value we calculated, which was negative 2.316 electron volts times 13.6 electron volts. 6 electron volts. Okay. And then that value, okay, good. There is no square in the bottom. That's maybe another possible mistake you can make. I was almost thinking there's supposed to be a square in the bottom because of this formula, but that's only for n. So realize that your negatives here should cancel out, and you should get a positive value that will satisfy being real for the square root. So let's take this, and we're going to do 13.6 on top. 2.6. And so with this we get, let's see, actually, wait a second. So 13.6 divided by 2.316. Okay. In the square root we get 5.87. It's not a whole number, and it's not going to just round up. But then if we square root the answer, let's see, something is not quite right with that. We're not getting an integer number with that. Let me check to make sure I didn't make any mistakes. Okay, so we have, let me see, 13.6 over 2.316, and then we have that. Yeah, that's not getting us a whole number for this problem. So 2.42 is not close enough to a value of n that's supposed to be an integer. So it might have been that we messed up one of these. So what I'm going to quickly do with these, if you want to also quickly check these for me just to make sure I got everything, and then we'll see what value we can get out of this. Let's see here. We have, okay, so we used hydrogen, we had the n equals 5 state, and we have, okay, 2.86 electron volts. So we lose 2.86. Let's make sure we calculate this right. So we have 13.6 over 25. Okay, it's 0.544. It's negative. And we subtract off 2.86. And then we get, okay, so calculator mistake. I figured it was a calculator mistake because we were getting like 2.44 when I calculated this. That's not just going to round down to 2. It should be pretty much on the dot. The mistake was that I forgot to write the minus sign in the calculator. So when you actually take these two, and I mean you look at it, it shouldn't be 2.3. It's actually going to be less than 2.86. It's actually 3.404. Okay. Whew, save that. 3.404. Okay, so we take that value, plug it in. This better be right. So now, take that value in the bottom, and then 13.6 in the top. Okay, so now what happens is the value I'm getting in my calculator without square rooting it is 3.995. It's pretty much on the dot 4, so that when you square root it, it's going to be practically 2. Okay, so I get 1.999. Okay, so at that point, because of rounding, because the problem only gives you 3 significant figures for the electron volt value, you're only going to get a value that's right up on 2 or something like that. So if you get a value like 1.99, then it's 2. Okay. So we get equals 2. Okay. And that's the answer for what we transitioned down to. Okay. This should make sense because we went from n equals 5 down to a lower energy state, which is 2. Okay, so it makes sense with the context of the problem. Okay. Are there any questions on this part of the problem before we move on to the next part? Let me know or give me a thumbs up. I'm going to quickly write into here. I need to make a habit of doing this because it's otherwise going to be hard for you to be able to tell me where to go. Okay, let's carry on. So, part B of this, find the radius and the speed of the electron in the initial orbit. Okay. Okay. This equation is one that I do not use that often. It's enough to the point where it's the first one I don't have memorized. So what we're gonna do is we're gonna just look up what the radius for a particular orbital is and the associated speed with that. So hang in there for a minute or two while I pull that up. Otherwise, you can just write it into the comments if you're able to. Let's look up. So radius of orbital. Okay. Okay. Hyperphysics is a pretty good website for this. Eventually, in the long run, on my website, I'm going to intend to try and put everything up on it. So maybe in the near future, my website will be one I can just reference to. Hyperphysics. So radius of orbital, hydrogen. Okay. Okay, so here. Bohr model. Okay. The topic that you do want to reference to for this when you're talking about the radius and the speed of the electron in a particular orbital, it has to do with the Bohr model, where you have that the electron is seen as something where it just whizzes around in a circle, pretty much, of a certain radius. So with that, let's see, Bohr orbit. Okay, here we go, found it. The equation is pretty simple for the radius. Okay, so what I'm going to do is, let me write it up here. Okay, so let me check if you guys have any questions before I erase part of this. So we have, okay, you have the velocity written out. Awesome, thank you. I think I found it at the same time, so if anything, we can just compare our formulas and just check that it works out, but I think you have it correct. So it looks like we're good on questions, so I'm going to erase part of this. So take out the Rydberg equation, and let's write the radius of the orbital. Now what will happen is you'll notice that even if you don't know the equation for the radius of the orbital, you should realize that the radii will decrease with lower energy levels or vice versa. So you know it should depend on the value of n that you're sitting in. But also if you change the type of atom you have, which is the value of Z, the atomic number, these radii will change also. So those couple of factors will go hand in hand with it. So the equation that we get for the radius of the corresponding orbital is going to be equal to, we have n squared a naught. I'll define what a naught is in a second, and divided by z. Okay. If it's not exactly written like this for you, it should still have the n squared and the z in it. A naught is a constant, so a naught is defined as the Bohr radius. Okay. So the Bohr radius is going to be the radius for the n equals 1 for hydrogen. Okay, so n equals 1 orbital for hydrogen. Okay. And the value of this, you're just going to use as a constant, is, so if you want to write it in scientific notation, it is 5.29 times 10 to the minus 11 meters. Okay. If we're just going to put it in standard units, it's that value in meters. Okay. So all we need to do to find that radius is we're just going to plug in the n value we're concerned with, and the z value for, in this case, it's hydrogen, so it's just 1. Okay. So let's go over here. Okay. That should be good. So we have that r equals, so in the question I think they want us to use 5, or is it 2? We want to use the, oh, it's the initial orbit. So the initial orbit is going to be n equals 5. Okay. So n equals 5. Let's switch this back. Okay. So 5 squared times 5.29 times 10 to the minus 11th meters divided by z, which is 1. Okay. So 25 times the Bohr radius. 25 times 5.29 times 10 to the minus 11th. Okay. So we get, and also a little note here, when you plug this into the calculator and you just get a value for this, you're going to get a value which has pretty much like a 1 on the end, because your calculator doesn't have enough space to write all the digits. So I would suggest that, again, make sure you know how to switch your calculator to scientific notation, so you won't get like something like 0.00000 and it ends with a 1. It's actually 1.32 times 10 to the minus 9th meters. Okay, because you're certainly going to get something here that is too small to write without scientific notation. So this is your radius. Okay. And that's the radius for the 5th orbital. Okay. That gets us the radius, and then let's calculate the theoretical speed of the electron in the orbital if it were to follow the Bohr model, which is technically incorrect, but it gives us correct results from it. So that's something good to conceptually remember. So you typed in the formula in there, and I believe hyperphysics has that as well, likely. Let me just make sure. Actually, it doesn't have it immediately available. So what I will do is I will actually reference to what you wrote, because it looks familiar to me. So let's use what you have written out, and I'm just going to check the units on it to make sure it looks good with the units. If you're doubting if something is right, a good thing to do is unit check it. So velocity for that nth orbital equals n h bar, that looks, or actually h, just h, that looks familiar, over 2 pi, and then mass of the electron and the radius of the orbital. Okay. So if we analyze the units on this just to make sure this is good, I'm going to do the very quick unit check on the side. Okay. N is unitless. H is in joules times seconds. Mass is in kilograms. Radius is in meters. We need to get meters per second out of this. In just quickly doing this unit check, you'll actually find that it should work out. So kilograms, meters. Okay. The kilograms go away. One of the meters goes away. One of the seconds go away. And actually you get meters per second out of this. So the unit check passes. If this isn't the correct formula, at least it's sane. Okay. So plug in values. We're using 5 because this just goes off the previous part. Planck's constant is 6.626 times 10 to the minus 34 joule seconds, all divided by 2 pi. Mass is going to be mass of an electron is the definition of this because we're talking about the electron in the orbital. So it has to be the electron mass. So 9.11 times 10 to the minus 31 kilograms. Okay. Should be a given value. And then the radius, which was previously solved for. So we have 1.32 times 10 to the minus 9th meters. This equals a velocity of, so we have that radius that we calculated times 9.11 times 10 to the minus 31 times 2 pi. That's in the bottom. And then do the top, 5, and then 6.626 times 10 to the minus 34. Okay, so the answer we get for the speed. Now, even before you get an answer, there's already a reasonable expectation that while the speed should probably be fast, very, very fast, it should never be larger than one particular speed, the speed of light. So if you're getting answers which are larger than the speed of light, it's probably not good. So if you know the speed of light is 3 times 10 to the 8th meters per second, make sure when you're solving for speeds that you ought to be getting speeds which are smaller than that. Otherwise, no bueno. So we have 4.38 times 10 to the 5th meters per second. Okay, that's less than the speed of light, so it seems okay. This solves out all the workout problems. Okay. Are there any questions on this problem before we move on to the multiple choice? We talk more about some of the conceptual details and then how to do some of those multiple choice quickly. Let me know or give me a thumbs up. The way I unit check it is mind-blowing. It's amazing what you can do in physics by using a skill you've learned from chapter 1. So, yeah. Okay, so let's see here. Let me quickly write some numbers on these. So if you do have any questions on these, you can just point me to which number I really should be looking at. Meanwhile, let's scroll to the other part. We still got a good hunk of time. In case you do have to dip out for some reason, thanks for tuning in so far. We'll otherwise keep going. So again, if you like what I do, keep on telling other people about this. I plan to do something on tomorrow or Tuesday as well. Let me know if there's a better time. Maybe instead of a specific time, maybe we should just do a night time like this again. Does nighttime sound good if anyone's interested in doing this at night again tomorrow or Tuesday? Let me know on that. But otherwise, anything helps me, telling your friends. And if you do care to donate, you don't have to. Again, remember, this is free. You can either Venmo me or Patreon. It's on my webpage. So let's do the multiple choice. So let's scroll down. Okay. Now time to do a variety of things. So doesn't look like we have any questions on anything previously, so let's take a look at that multiple choice. Let's see. Let's start with number 1. So in this we have, what is the surface temperature of a star given its radiation peak occurs at a frequency given 1.06 times 10 to the 15th hertz. Okay. This question right here falls under the topic of blackbody radiation. Okay. I'm going to briefly point out what happens with that, and I'm going to give you what will solve this pretty quickly. Okay. So for this one, topic will be blackbody radiation, so multiple choice. Problem 1. Okay, so blackbody radiation. Okay. So the idea is that you have an object and it's going to be at a certain temperature. Okay. And at that given temperature, it's going to emit light in every direction possible from it. So that electromagnetic radiation that gets emitted from it, that we're referring to as blackbody radiation, there's a whole spectrum of light that gets emitted from it for different wavelengths. So in a lot of the problems that we do, such as like the double slit experiment, single slit diffraction, a lot of those problems that you'll do will most likely deal with one wavelength, and that is called monochromatic. Mono meaning one and chromatic is color. Blackbody radiation is going to deal with a whole spectrum of different wavelengths that get emitted based on its temperature. So the blackbody radiation curve is this plot. This is a plot that you should try to remember visually. It will help you to understand conceptually what's happening as you change the temperature of the object. So what will happen is, let's say that you start with a lower temperature object. Okay. Now take, for example, you take, let's say you go to like a blacksmith or something like that, and you take a piece of metal and you have them turn it into some piece of equipment. So you know how they will heat it up, they'll make it into something molten, they'll cast it into something like a sword or whatever. If you've ever noticed that when you warm up an object, it'll initially not be glowing. So let's say you take a black object, it's not glowing. But as you heat it up, it'll start to visibly emit light, and the first color you're going to see is red. And then it's just going to continue through the spectrum, orange, yellow, and you actually do not see green, you see white, which is another conceptual question I will touch on, just in case you get that in your multiple choice. Then blue, then if it gets really that hot, violet, etc. But what will happen is, on this graph that you should conceptually remember, is a plot of the intensity of light, how bright it is, versus now in this, let's just say we deal with the frequency when we plot this. Okay. In fact, in this question, I think they give us a particular frequency. They give us a frequency of 1.06 10 to the 15th hertz. So let's plot this versus frequency. The general shape you should be expecting kind of almost looks like a bell curve in a way. Is this like almost like a grade distribution, but it's a little bit skewed. It has a peak, but then it has a longer tail that goes out like this. Okay. So there's going to be a point in which the light is most intense, so it has a very high intensity at a particular frequency. Okay? Now this curve, let's just say for example this will be a number, let's call this T low for lower temperature. It could be something that's relatively hot to us, but it could be low on the lower end of the temperatures that it could possibly range for. Let's say we have a lower temperature. What will happen is the peak will sit somewhere around a particular frequency. So this frequency, let's call this the peak frequency, F peak. Okay. This peak frequency corresponds to the maximum intensity or brightness you'll see for a particular frequency or wavelength, so you can think of it as color, basically. So let's say if we have a lower temperature, what might happen is this frequency might correspond to a color like red or something like that. So what will happen is you'll see a bunch of red light being emitted, but this intensity curve suggests that if you go further away from the peak frequency, the light gets dimmer for that particular color. So if the peak was at red, for example, anything that's on lower frequencies such as infrared, radio waves, microwaves, all that stuff doesn't really appear too much. Same thing on the other side. If you start going higher in frequency, you start going to the other end of the visible spectrum to like violet, ultraviolet, and beyond that, also doesn't appear as much. So for this, what will happen is you'll see dominantly red. But as you continue to increase the temperature of it, what will happen is the curve will start to go up higher and start to shift like this. This will be like a middle ground temperature. So it's a higher temperature, so you get a bigger intensity, but the peak actually shifts over more. Okay? So it'll be the F peak for that particular temperature. And this will just continue to happen as you continue to raise the temperature. But this actually explains why the color that you notice with your eye will change as you heat something up. So notice that because the peak shifts to the right on the graph, the frequency increases. That means that the dominant color you see will have a higher frequency. So as you warm it up, it will go from red, which is the first color you see, to orange, which has a higher frequency, yellow. And the reason why you don't see green on certain objects that are hot is because you have a lot of the stuff on the lower end of the visible, reds, orange, and yellows, and then you have also a lot of blues and violets mixed in. So when you mix all the colors, you don't actually get green. You see white with your eyes. So the order ends up being red, orange, yellow, white, and then it starts to be blue and then violet. Okay, that's the principle behind this. The actual thing you need to compute the answer to this specific problem. So again, this was good conceptual details for if there was a variation of this problem. The equation you need is that the frequency peak equals a given value over the temperature. This value, I believe, is somewhere around 5 times 10 to the something. I need to quickly look that up. It has no particular name, but this is a very simple equation that we just need to solve. Okay. So the value that belongs in this equation, it's called Wien's law, W-E-I-N. Wien's law for frequency. Okay. So Wien's law says that this value is going to be actually it's not 5 point something. I think it's 2.98 or 2.89. We can round that. So let's say 2.90. So 2.90, and then times 10 to the, we have minus 3. And then the units are going to be in meters times Kelvin. This is supposed to be a given value. When you have it on like a formula sheet, it'll just be already there for you. But you're going to use this equation, and in this question they're just asking for the temperature. So all you do is solve for the temperature. So it's 2.90 times 10 to the minus 3 meters times Kelvin divided by frequency peak. Okay. We are given the frequency for the peak. It's 1.05 times 10 to the 15th. So 2.90 times 10 to the minus 3 meters times Kelvin over 1.05 times 10 to the 15th. And Hertz is going to be 1 over seconds. Wait a second. That's, oh, this equation gives us, it's not the frequency peak, it's the lambda peak. That's why that number doesn't look familiar. 1 second. Ah, that's right. Okay. This is why this doesn't work out. The reason why I could tell this doesn't work out, why something seemed off to me, is not because the number didn't seem familiar to me. It's actually because of the units. The units just don't, they flat out don't work out. Again, you'd be surprised how well a unit check will save you from getting things wrong. The value in the top was meant for the wavelength peak. If you actually use the frequency peak formula, it says it's 5.88. That's the value I actually remember. 5.88 times 10 to the 10th, and the units will be hertz per Kelvin. Okay, now in this, now with this right here, you end up with the correct units. So I'm just put quotes just to emphasize it's the same thing. But if you put the units in, hertz over Kelvin, and the bottoms in hertz, the units work out here, and is it hertz over Kelvin? Oh, times temperature. Okay. Okay, so we have times temperature. Okay. That's the other thing, is that if you actually had it like this, you would get 1 over Kelvin, which is still not right. So it's actually times the temperature. So we actually need to move this number over to here. So let's fix that. So the temperature is actually frequency peak over that number of 5.88, 10 to the 10th hertz per Kelvin. So that's 1.05 times 10 to the 15th hertz. Okay. And then 5.88, 10 to the 10th hertz over Kelvin. Okay. The units now work out. The fraction in the bottom for the units flip. You get hertz over hertz, it cancels, and you get Kelvin on top. So it's now a temperature in Kelvin. Okay. Again, I was able to fix this problem only based on unit checks. Okay, always check your units. They're very important. Calculate this here. Okay, so we have 5.88 times 10 to the 10th. Okay, that's in the bottom, times 1.05 times 10 to the 15th. Oops. Okay, that will give us 1.79 times 10 to the 4th Kelvin. If you want that non-scientific, that's going to be about 18,000 Kelvin, and it's the temperature of a star. It's going to be very, very hot. So for our choices, we had 17,000, 14,000, 20,000, 18,000. Okay, so the answer is going to be D in this case. It's going to be about 18,000 Kelvin. Okay, so answer is D. Okay. Let me know if you have any questions relating to this topic of blackbody radiation. Okay. Let's scroll down to this question. So the next question is a single slit diffraction pattern. Okay, so we're dealing with single slit. We have the pattern formed on a distant screen. Assuming the angles involved are small, okay, that's always going to be the case in these, or most of the time it's going to be the case in these problems. By what factor will the width of the central bright spot on the screen change if the slit width is doubled? So this just relies more on knowing conceptually from the equations what happens if you do this to this thing. So what we're going to do is we're going to write out the equations for a single slit, and we're going to figure out what will happen to the central bright spot in its width. Okay, so let's switch back here. Now, in the single slit here, so problem 2. Okay, so single slit diffraction. Okay, so the problem was asking about the width of the central bright spot. So remember that the pattern to this, if you looked on the viewing screen, okay, so you have your single slit and you have the viewing screen. Remember that the central bright spot will be here. That'll be alternating between dark and bright, so it'll be dark, bright on either side. When you're talking about the width of something along the screen, really what you're saying is the distance from the center to something anywhere. In this case, it's to the end of the bright spot, which is where the first dark spot is. The distance along a viewing screen is always used as y in this problem. Okay? So the width of the central bright fringe is just directly related to what the value of y is. In fact, it's actually just 2 times the value of y if you find it for the dark spots on the either side. Regardless, as long as you know it's going to be directly related to the value of y, we just need to find how y relates to the width of the slit, because in the problem they say that we are going to change the width of the slit. So we need to find out how w, the width, affects the value of y. So we have that for y, we have tangent theta equals y over L. That's one of the equations, and that's the one that directly talks about y, which is dealing with the width of something along the wall. But then this doesn't relate it to the width of the slit. Where you're going to now relate it to the width of the slit is by using the other equation with the width. Say that 10 times fast. D sine theta, or not d sine theta, w sine theta is what they call it in this equation, equals m lambda. Okay, so what we're going to do is there is something called the small angle approximation, which is a long story of how that works, but the gist of it is that you should take away that small angle, small theta approximation, means that sine of theta is approximately the same as tangent of theta, which is approximately the same as just writing theta. Okay, so that means everywhere we see sine and everywhere we see tangent, we're just going to write theta. Okay, in other words, in these equations, what we should now write is that theta is approximately y over L, and we should also write from the other one, w times theta is approximately m lambda. Okay. All we're doing is we're just calling the sine and the tangent theta. Okay? That's what the small angle approximation is. This just makes everything easy. So all we got to do is solve for y in terms of w. So all we have to do is take the theta from this equation, drop it into here, and then solve it for y. So theta is approximately m lambda over w. What you're going to do is you're going to take this and plug it into theta over here to get rid of theta, and now let's just rewrite what this is now. So plugging this in, we have m lambda over w is approximately y over L. Okay. Solve it for y by just moving L over. In fact, you don't even really need to do that technically at this point because you already have something that relates y to the width of the slit. So the thing that you really need to care about here is if you look at y and you look at w, what happens to the value of y as you change the value of w? So in the problem here, it states we are going to double the width of the slit w. So if w doubles, then what will happen to the width of the bright spot? So all we need to do is take a look at this. So if w will increase by 2 times, okay? Increasing something by a factor of 2 in the denominator makes the whole number smaller by twice the amount. So because y is in the top here and it's inversely proportional, we should actually notice that the value of this will decrease by 2 times. So that means that y, which is related to width of bright spot, will cut in half. Okay, so the answer to this one would be cut in half, which is B. So answer is B. You have a question. Would it be safe to say the sine of theta will decrease when W increases? That will be a true statement because they're on the same side of the equation. If you moved W over, you would actually divide it in the equation, and it means if you increase it in the denominator, the sine of the angle would increase. So that would be true. Okay. Let's see here. Let me scroll down to so we can see 3. Okay. For 3, this one we could just discuss conceptually. I don't need to do much with it. Number 3 says an important implication of the uncertainty principle discovered by Werner Heisenberg is, so there's a few options you'll notice here. There's a couple which are obviously not true if you even read the uncertainty principle before. It's nothing to do with the time that we're talking about. There's answer A talks about the future based on the present, and the last choice E, knowing the present, so it has nothing to do with that. Okay, the uncertainty principle has to do with, for example, when we talk about the position and the momentum of a particle, such as an electron, you cannot be fully certain about it exactly. So if you look through these, so B says above a certain particle size, de Broglie waves are so insignificant that they drop to 0. C, there is an uncertainty in knowing the position and the momentum of the electron simultaneously. That actually pertains directly to what I just said about what the uncertainty principle is written out with. So we're going to roll with C, and then the last one was D, very small particles moving at very slow speeds, containing vast quantities of energy. That has nothing to do with uncertainty. The Heisenberg uncertainty principle is the title of it, so you want to be looking for stuff having to do with uncertainty. So let's say that the answer is C. There is uncertainty in knowing the position and the momentum of the electrons simultaneously. Okay. And again, with this stuff, I'm just going to keep on going. If you have questions at any point, just slow me down, let me know. I'm going to scroll through one at a time. For number 4, okay, we have monochromatic light. So again, that means one color or one wavelength or frequency. Falls on a metal surface and electrons are ejected, okay? That should automatically ring in your head photoelectric effect. There's a metal surface and electrons are ejected. That is photoelectric effect. If the intensity of the light is increased, okay, remember we talked about the 2 main principles behind this, which one of them was talking about the intensity or the brightness of the light. How does it affect the experiment? Versus the other one was changing the frequency or the wavelength of light, which has to do with the energy per photon. So those are the concepts you need to know to be able to answer this question. If the intensity of the light is increased, what will happen to the ejection rate and maximum energy of the electrons? So remember that the intensity of light or the brightness does not affect if they get ejected or not. That has nothing to do with it. So the maximum energy of the electrons is unaffected, okay? Because the maximum energy of the electrons or the maximum kinetic energy of the electrons directly has to do with, okay, so we have photons hitting it and that determines if they eject or not. The more energetic the photons are, in other words, the greater the frequency or the smaller the wavelength, the more energy you can give the electrons. But remember that intensity is just saying you're throwing more photons at it. It does not at some point eject electrons from not ejecting it. So the second half of the answer is same maximum energy. So the answer is either A or D. Between A and D, it's either going to be the same rate or a greater rate. So the thing is that if you do flood the experiment with more photons, which is to say that there's a more bright beam or higher intensity, given that they are going to eject, so based on the frequency, they do eject. Given that they do eject, you can increase the number of electrons that get ejected. So again, not going to determine if they do eject. So we can say greater rate, okay? The answer would be D. Okay. Hopefully that made sense. Let me know if you have any questions on that one. I'm going to scroll down a little bit to 5. Okay. So 5, this one you can see there's a current and there's some loops. If you've done a lot of these problems, you can kind of already expect something with flux and Faraday's and Lenz's law, which have to do with changes in flux and producing voltages and an induced current. In here it says the wire in the figure carries a current I. So in this figure it says it's left to right, okay? It's increasing with time at a constant rate. Okay, so the current's getting stronger, which actually also means something else gets stronger. Remember conceptually that currents produce magnetic fields around them. So if you increase the current, you're increasing the strength of the magnetic field. And I will, I'll switch back and I'll write the equation in a second. There are 3 loops, all in the same plane. Okay, so these are 3 separate loops. What is true about the currents induced in each of the 3 loops shown? So in here, they talk about the directions of the currents induced in the loops or no current being induced. Now, if you understand the idea of Lenz's law, which is paired with Faraday's law, and that the core of it is based on a change in magnetic flux. The change in magnetic flux, or the magnetic flux itself, is based on 3 factors. I'll switch over and I'll actually write these out because this is a pretty important principle to understand. So magnetic flux is what we need to look at here. Okay, Okay, the equation is the magnetic flux equals the product of the magnetic field, the area, and cosine of some angle, which has to do with the way that the loop is oriented compared to the direction of the magnetic field. Okay, that means there are three factors that control what amount of flux goes through like your loop system. But the part that's going to matter is, do any of these things change? So according to the core of Faraday's and Lenz's law is that, so for these laws, Faraday and Lenz's, L-E-N-Z, Lenz's law. The core of it is it's based on a change in flux. Okay, in other words, delta V. Okay, that means that to have a change in flux, one or more of these three quantities in the equation has to change. Now, in our particular problem, we have a current carrying wire that has a current from left to the right. Okay, so label that the current I. You should already know by seeing a current here, there's going to be a magnetic field around it. There's a right-hand rule that was associated with finding that magnetic field direction. So pretend that this is my current here. I need to stick my thumb in the direction of the current, and I'm going to curl my fingers around like I'm grabbing the wire. So I would grab around like this. Notice that in grabbing it, you would have that curls around like this. So that means if you're doing this motion here, the magnetic field lines will wrap around it circularly this way. So if you're looking at a page, when you do this right-hand rule, it's going to come out of the page on top and it's going to go into the page on beneath it. Okay, so that way is the current, around, out of the page, and into the page. Okay. So on the top of it's out of the page, remember the notation is dots for vectors that are out of the page. That's my magnetic field. And everywhere below it's X's to mean that it's into the page. Okay. Once we have that, we also need to understand that the strength of the magnetic field, how strong is that magnetic field in units of Teslas, is equal to U naught, some constant, which is given, times the current I divided by 2 pi r, where r is the distance from the wire. Notice the most important thing in this equation, in this particular problem, is that the current was said to increase over time. If the current increases over time, the value of I increases, which means the magnetic field strength increases. Because the magnetic field strength increases, that means the magnetic flux increases. And since Faraday's and Lenz's law is based on a change in flux, we know that there is going to be a result for this. So when we go back to the problem here, okay? So looking at the problem again, the first answer is automatically wrong because A says no current is induced in any loop. We know that there is a current induced in at least one of the loops because there is a change in flux. Anytime you have a change in flux in the system and there's a loop that is capable of having current run through it, the change in flux will cause an induced EMF or voltage according to Faraday's law, and it will produce an induced current according to Lenz's law, which you can find the direction of. So the answer cannot possibly be A. Now the other ones, so B says the currents are clockwise in all three loops. The other choices are basically saying one of them is clockwise, one of them is counterclockwise, and one of them has no induced current. You can already tell from the diagram that the one in the middle, loop B, has to be the one with no induced current. And the reason why is, if you want to look at it this way, see that half of the loop is in the region above the wire, which is magnetic field out, and half of the loop is into the region where magnetic field is into the page. So the effects kind of cancel out on both sides. So the magnetic flux for B kind of cancels out, so you ultimately see that there's no current through the loop B. So when you see it that way, the answer choice B is not possible because it's saying it flows clockwise in all of them. So we know that there's no current in B because of this principle. So it has to be between the last three here. And notice they all say loop B has no induced current in it. Okay. What's going to determine the answers to A and C is based on your knowledge of what happens with Lenz's law. So here's a very, very quick rundown of what happens with that. So what I'm going to do is I'm going to go back here, and I'm just going to go through the motions of showing you how to quickly, as best as possible, get the direction of the current for the remaining two loops. Okay. This is technically a 5-step process to find this, but I'm going to boil it down as quickly as possible so you can get the answer quickly. Okay, so the idea is you're first going to ask yourself, which way does the magnetic field point? Okay, we're going to refer to this magnetic field produced by something else as the external magnetic field. Let's do it for the top loop, for instance. The magnetic field points out of the page. What that means is the magnetic flux is out of the page. It's flowing out. Okay. Now, from there, what we need to ask is, how does it change over time? Because the most important part about these laws is what's changing. So we have something that's pointing out of the page, but notice that the current is increasing over time. So what happens is the magnetic field strength is increasing over time. So think of it as you have this magnetic flux vector pointing out of the page, which is the flow of the magnetic field, and the magnetic flux is just getting stronger, so it just grows bigger and bigger and bigger out of the page. According to Lenz's law, it's going to produce a current in the loop to try and oppose the change. So if something is growing out of the page, you're going to do something to try and oppose that behavior. So as it grows bigger out of the page, you don't want it to grow bigger, so something is going to point the opposite direction to oppose that growth. So imagine that there's now something pointing into the page through the loop. Call that the induced magnetic field. Draw a separate vector for this. This vector is called the induced magnetic field or magnetic flux. Okay? It's the magnetic field or flux that will oppose the change. Notice in this specific problem, it does point in the opposite direction of the magnetic field, but that's not always true. There's another problem where it will point in the same direction, because if you take something away, you want to put it back, so you put something in the same direction. Okay? So it's not always in the opposite direction of the field. This points into the page, and once you're able to get this induced magnetic field or flux, you can just basically stick your thumb into the direction of that induced magnetic field or flux, wrap your fingers around, and that's the answer. It's clockwise. Okay, so for the top loop, we're going to say that the induced current goes clockwise. Okay, I'm going to quickly repeat this process for the bottom one, just to see that we can agree on an answer. So the bottom one, quickly again. First, look at the direction of the magnetic field or flux, external. It's pointing into the page. Okay, so into the page. Because the magnetic field is growing over time, we have something that's going into the page and increasing, but Lenz's law says to oppose the change. So you're going to point something in the opposite direction in order to attempt to decrease it instead of increase it. So now you have something that's pointing out of the page. That's the induced magnetic field or flux. Okay. You can do a right-hand rule on this. Stick your thumb in the direction of the induced magnetic field or flux. Wrap it around. Notice it goes counterclockwise in this case. Okay. So we have counterclockwise for the bottom loop. Okay. So clockwise, middle loop is 0, and last loop below is counterclockwise. And let's check the answer for that. Okay. So based on the choices that we have here, the answer would be, looks like C. Loop A is clockwise. Loop B is no induced current, and loop C is counterclockwise. So the answer is C to this one. Okay. Because I want to make sure that when you see this problem, you absolutely get it, because it's almost guaranteed that you'll have one of these problems on the multiple choice because it's such an important concept. I'm going to give one more minor example, which will only be basically one of the loops, but I want to show you a case where it's not in the opposite direction. It will end up in the same direction. Okay, so the very, very quick similar example to this that you could see in place of this problem on the exam is, instead of doing a current which is increasing over time, let's just change it to decreasing over time. Okay, so if we were to do it with decreasing over time as opposed to increasing in this one, so this one's increasing, if we do decreasing current, okay, so decreasing current is just a way of saying the magnetic field strength, and hence the magnetic flux will decrease over time. Okay, so we know there is a change in flux. Now, if we were to do, let's say, only do the top one, just to demonstrate the concept, okay? If you only do the top one, and you can assume the bottom one's in the opposite direction in this case, we have that the magnetic field is going, out of the page, like this, everywhere. This is the external magnetic field. Okay, so what we're going to do is we're going to go through the same steps one more time. Magnetic flux or magnetic field external is out of the page. But in this problem, we're saying it's decreasing. If it's decreasing, what you're doing is you're taking the vector and you're shrinking in size or taking it away. But Lenz's law says to oppose what the change is, not the direction. So if you're taking it away by decreasing it, the opposite of taking away means to put it back. You don't put something back by pointing something in the opposite direction. You put something back by helping it to grow. So you point something in the same direction as it. So unlike this one that we did previously, these ones were in opposite directions. Since we're trying to prevent it from decreasing, we point something in the same direction. So that means that the induced magnetic field in the loop is now in the same direction as the external one. Be induced. Okay. Because of this, we're going to get the opposite answer as this. So if we quickly do this, thumb in the direction of the induced magnetic field, that's out, curl it, that's counterclockwise. So the answer here for this hypothetical example is counterclockwise. Okay. Make sure you know how to do these ones. Practice it with different scenarios. It doesn't have to be with this particular scenario. Make sure you know how to deal with things increasing or decreasing. Maybe you could have the loop is moving closer to somewhere or further away from somewhere. There's a variety of different cases you can do to change the flux. So make sure you study those problems. So that was 5. That's a more challenging concept. It's one of the hardest concepts to understand in 100B, just no calculations, just pure conceptual detail. So it's not a surprise that a lot of people do struggle with this one. So the answer was C for that one, for the original example. Well, how many do we have to get through? We have 6 all the way through 12. Okay, it's not bad. Let's see if I can push through a little bit more. I don't know when you all have to dip out. I can go on a little bit longer. Let me know if you got to dip out, but I'm going to try to push through a little bit more of this at least. If anything, we can just pick up tomorrow or Tuesday, but let's at least take a look at a couple more. What I'm going to do is I'm going to probably actually pick out a couple I could do more quickly because it's already past midnight. Let me scroll through these. We have 6, 7, electromagnetic waves, proton, this one's voltage. Number 7 is very quick. Maybe we'll just quickly get that one. Electrons propagating, this is a de Broglie wavelength. This one, 10, is actually a bit longer to explain. I would save that for the next live stream. So that one's a little bit harder to explain. 11, this is right-hand rule on 11, and then this one is nuclear physics. So I'll pick out a couple of shorter ones, and the rest we'll either do Monday or Tuesday. If you want to come back Monday or Tuesday night is my guess. So let's see here. You were talking, okay, so you're saying number 6. Okay. Number 6, let me see here. The strong nuclear force. Okay. Now, for number 6, what I'm actually going to tell you for this one, particle physics isn't actually my area of expertise, and I haven't done much with it. Number 6 is an answer that I could give you probably tomorrow with better confidence. I could whack at something right now, but I don't want to tell you something that's off because I haven't studied this topic that much. But I can email you an answer to that, and I'll talk about it next time is for this particular topic. I do know some stuff in nuclear physics and particle physics, but relating to like strong nuclear force, I haven't done much with it. So that one I can't tell you much about right now. Number 8. Yeah, so I will make sure to give you an answer to number 6. Number 8, let's see here. Number 8, a proton. Okay, yeah, okay. So I wanted to see if I could do this one. So let's I'll do 7 real quickly right now because that's just quick answer, and I'll do 8. 7 is when 2 coherent electromagnetic waves are arriving at the same point in space 180 degrees out of phase, their interference is destructive. Okay, the answer is destructive. Remember that a wave or a wavelength, just picture a sine wave, so it goes up above the axis and it goes below the axis, and that's a wave. 180 degrees is half a wave because it's half of a full circle, which is 360. When the waves are half a wave out of phase, or 180 degrees, what it means is that if you shift the wave by 180 degrees, the negative part of one wave will line up with the positive part of another wave, so they're perfectly lined up in the opposite direction. So what happens is they cancel out, and it's called destructive. If you wanted to change this to a different variant question, you could change it to 0 degrees. In other words, they perfectly align. Or you could say 360 degrees, which means they just line up again. Any multiple of 360 degrees means they're actually in phase and they add constructively. So those will be the 2 possible answers for this problem if you did 180 or any multiple of 360. Okay. Let's see. So number 8. Number 8, a proton drops from a potential of 3,000 volts to a potential of 1,000 volts. Okay. Remember, one of the most important things with electric potential is the difference in potential. If you go from a place of 3,000 volts to another place that's also 3,000 volts, the potential difference is 0. Nothing will happen based on a potential difference of 0. The potential difference is also known as the voltage. So if I ask you what is the voltage in this problem, the voltage is actually a difference. You're talking about a difference of 2,000 here. So the important number to use here is 2,000 volts. How much is the change in potential energy of this proton falling through this potential drop? So let me switch over here and I'll show you the formula you need and conceptually how you get this. So this is not too long. This is very quick. So this one, you need to go back to the chapter with potential energy and electric potential. So a couple of things is when you want the electric potential energy, the letter we use for that is U. delta U is the change in electric potential energy. And when you're talking about a single charge moving through a potential difference or a voltage or an equivalent term to that, the simplest way to write this is Q times delta V. That's it. So U equals Q times V. So here, delta V is defined as the potential difference, or the equivalent term is voltage. Okay, you could do V like a V final minus V initial. So that's why I'm saying when you have the 3000 and the 1000, you need to actually get in this problem that the absolute value of it is 2000 volts. Okay, so that's the numerical value you want to be using. And with a charge, so what happens is it says in this problem how much is the change in potential energy as the proton is falling through this potential drop. Okay, so the key phrase here, let me go back to this quickly just to highlight the key phrase that tips off what you're supposed to do. So other than the first part, which we established the difference is 2000 volts, the proton, which is important because versus an electron, things are different between protons and electrons and what happens. But for the proton, the key phrase here you need to pay attention to is potential drop. Okay, potential will drop, meaning that, because if you're wondering, okay, do you go from 3000 to 1000 or 1000 to 3000? Well, the drop suggests that it goes from 3000 to 1000 volts. So what this really means is that when you are writing out the delta V or the voltage, the absolute value is 2000 volts. But delta V in this problem actually is negative 2000 volts because of potential drop. Okay, the key word is drop. So we're going to use a value of negative 2000 volts, and you're going to also use the charge that you're talking about, which is in this case a proton, so it's a positive charge. So delta U, the change in electric potential energy, is charge, which is 1.6 times 10 to the minus 19th coulombs. Okay, that's a given because this is the charge of a proton or electron. That should be automatically known. Times negative 2000 volts. Okay, the answer is going to be 3.2 negative times 10 to the 1, 2, 3 places minus 16th joules. Okay, so the negative sign on this, because it's the change in electric potential energy, the minus sign signifies that you've lost potential energy. Okay, so the answer for this one is going to be A. Okay. So A is negative 3.2 times 10 to the minus 16th joules. Notice that there is a trick answer in here. The trick answer is going to be basically the positive answer, which is basically a way of saying you need to pay attention to your signs. Okay. So A for 8, and I think that's probably good for tonight. Are there any other quick questions on actually on any of these that we just did? So like 8, I would say. Otherwise, any questions on what we're doing Monday or Tuesday? Do you have any times that you would like to see more stuff done? Maybe tomorrow night or Tuesday night between you guys? And you're welcome, by the way. So yeah, so I'm thinking now, I put up a poll over the weekend, but I don't think anybody put any responses on the poll, so I'm contemplating if I should put up another poll. So I don't know if you want to just give me a quick time frame for those of you that are here right now, and we'll just roll with that. My guess is that based on everything, it should just be Monday or Tuesday night. But if you want to drop a quick time frame right now, I can just set that up right now. Okay, you're saying Monday or Tuesday night. Okay. Any other quick input before we call it a night? Tuesday, you're done. You're down for the whole day. Monday, Tuesday night is good. So far, the nights are looking good. Okay. With that, what I'm thinking I'm gonna do is let's aim for tomorrow night. So what I'm gonna do is I'm gonna put the information up on my website on the front page. So when in doubt, go to the front page and you'll find the information. It's probably gonna be tomorrow night. We might just go for like a couple hours or something like that, not 3 hours or something like that. If you want me to email you it too, I could do that too, but otherwise just go to the front page of my website and that's where it'll be, and you'll just click on the banner at the top and it'll take you straight to the live stream link. So cool. We'll start with tomorrow night and then we will go from there. Cool. Hope you all enjoy the rest of your night and thank you for tuning in. Again, let anybody you know so we can go over more stuff and we can pull in more people and help more people out. So yeah. You're welcome. Have a good night, guys.